Hey guys, welcome to 5.3 for science. So today we're going to be talking about potential energy, but we need to take the first couple of minutes and talk about what we learned in 5.2, which was about the forms of kinetic energy. Obviously, kinetic energy is the one where the energy is in motion. We have the translational translational kinetic energy, where the motion is from one place to another place. It's translating itself there. And then you have the circular motion, that something is going around in a circle. And then you have the rotational motion, which is that the thing is not actually moving in a circular form, but that the axle or something inside of it is moving around, causing a circular motion. Okay, so it's not the same as circular motion. Circular motion is where you have one thing and it goes around in a circle. Like, for instance, let's take the Earth. Okay, the Earth goes around the sun. So here's the sun, the Earth goes around the sun here. That's circular motion, right? But it's also spinning on its axis, right? Every day it's spinning on its axis. That's rotational motion, okay? It's not going in a circle at that point. It's turning like this. It's rotating, okay? So that's the difference between the two. So let's quickly go through what you were supposed to do on your 5.2. If you look at page 118, we had done number 1 together. I told you to do number 2 and number 3, and then we were skipping number 4. So if you look at number 2, the answer that I got for that one is 424.9. The way that I got that was that we used our kinetic energy formula, right? E equals 1/2 of mass and volume squared, okay? So it says an object moving at 10 kilometers per hour has a kinetic energy of 10. Okay, so we have 10 equals 1/2. Didn't tell us our mass yet, but this should be 100, right? So I'm looking at my notes just to make sure that that's how I got it. Oh, no, I'm doing number 1. Oh, pardon. I was like, that doesn't seem like anything like I did yesterday. Okay, here we go. Let's do it again. We have our thing. We're on number 2. My board got ugly. Okay, at its current speed, a vehicle has a mass of 2. Okay, so there's our mass of 2. And has a kinetic energy of 850. Okay, so then we have V squared here. What is the kinetic energy of a 1 megagram vehicle moving at the same speed? Okay, moving at the same speed. So you first do this, you have to find the speed. Okay, so kinetic energy is E, which is 850, 1/2 times the mass is 2, V squared. Okay, once you get all of that, your velocity, is basically what happens is 1/2 times 2 is 1. So now you have 850 equals V2. So you take the square root of V, you take the square root of 850, and V equals 29.15, okay? So now you go back into the equation of kinetic energy. With a mass of 1, right? The velocity is 29.15, but remember you're going to have to square it, which is what I forgot the first time I did it. And then when you multiply all this stuff together, you're going to get 424.9. Okay? So that's going to be number 2. Number 3 you think would be harder, but it's actually super easy. Calculate the kinetic energy so you write down kinetic energy of a 5 kilogram, that's your mass, object moving at 4 meters per second. So that's going to be 16 because 4 squared, right? And you have 1/2 equals that. So you have basically 2.5 times 16, and your answer ends up being 40. So your answer number 3 is 40, okay? If you look at your section review for 5.2, let's go through those really, really quickly. Okay. You have define kinetic energy, number 1. That's the energy of motion. Number 2, what is the simplest form of kinetic energy? The book said that was whole body kinetic energy. Number 3, what is the simplest form of motion? That's translational motion. That makes sense. It's from one spot to another spot. What is motion in a circle with the center of the circle outside the object? Okay, so that means that like it's going around in a circle for real. That's circular motion. But the other one would be and number 5, what 4 factors affect rotational kinetic energy? Okay, if you look at page 119, in the second paragraph here, they're going to start talking about what affects rotational kinetic energy. The very first 2 things are mass and speed. Look what it says. As with translational kinetic energy, increasing either the mass or the speed of rotation increases the rotational kinetic energy. Okay? Speed is how far the object rotates in a certain time. You would learn that in advanced math, rotations per minute, and you would be using 2 pi, 1 pi instead of angles like we use for things that we're graphing right now. But we're not going to get into that in this class. And increasing the speed has a greater effect on kinetic energy than increasing mass. Okay, we learned that the last time. So you have mass and speed. Also look at the next paragraph. Size of an object affects its rotational kinetic energy. Okay. It says if 2 solid spheres have the same mass but have different sizes and both spin at the same time, the larger the sphere will have more rotational kinetic energy. And the object's shape affects its kinetic energy, which is the one down here. It says if a ring or anything of all the same mass and radius are rolling along a surface at the same time, the 3 objects will have different rotational kinetic energies because of the different shapes. Okay, so it's mass, speed, size, shape. Okay, now let's look at the application. Number 1 says a World War II era Sherman M4 medium tank had a mass of 30,300 kilograms and a top speed of 39 kilometers per hour. What was its kinetic energy if it was traveling at top speed? Okay, well that's easy. I'm not going to actually get the calculation for you. I'm just going to show you how we set it up. But you would have set it up like this, using the formula. The top speed is what you're going to use for your velocity. So it would have been like that, 1/2 of the mass times velocity squared, okay? And then number 2, a wandering albatross is flying at a speed of 2.8 meters per second and has a kinetic energy of 35. What is its mass? So what are you going to do? The E we have is 35 equals 1/2 times mass times the velocity, which is 2.8 squared. Okay, and then you just solve for M. So those are your answers for 5.2 and a little review on that. Now let's get into 5.3 and what we need to understand, okay? It says the fundamental forces and potential energy. There are 4 fundamental forces in nature that they're going to give you today, which is gravitational force, if you look at page 120. Then number 122, weak nuclear force. Also on 122, electromagnetic force. And number 123, strong nuclear force. And you can see that in the table right here on page 123 with some information there about those. Okay, so starting back here on page 120, the first thing that you need to understand very, very well is the difference between kinetic energy and potential energy. Potential energy is the stored energy, okay? Think about what the word potential is. If somebody says you have potential, that means that you have all the ability to do something well. But the potential is the ability to do it. It's not the actual doing of it. When you go to do that thing, in science, it's going to be converted into kinetic energy. So that's what you're going to be seeing today, you guys, in this section, is that potential energy has to be converted into kinetic energy for it to do anything. But the potential energy is very important, because if the object doesn't have enough potential energy, then how is it supposed to do the kinetic energy? It cannot. Remember that energy cannot be created nor destroyed, so it always has to be being transferred. So if you don't have any potential energy in the object, it's not going to do any kinetic energy. There has to be that conversion over, okay? So potential energy is the energy stored in something to do something when it's converted into kinetic energy, okay? And it's stored in there based on its position. It says right here, potential energy is the energy associated with the position of an object and the forces acting upon it. Well, what are those forces? Where does it get its potential energy? That's what it's talking about. From the four fundamental forces in nature that scientists have discovered, okay? The very first one being gravitational force. The gravitational force is one of the weakest. If you look at page 123, table 5.1, it's going to go from the weakest to the strongest. So the weakest one is the gravitational force. Why? Because where we are on Earth, the gravitational force between objects, it doesn't affect us very, very much, except from the gravitational force of the things outside the Earth. Okay, so for instance, the fact that the sun is so big, it attracts all the planets to it. I think that is fascinating. Let me see if I can find the sentence. You guys are going to read it anyway. Right here. The sun's gravitational force holds the entire solar system together, okay? In the solar system, yes, gravitational force is huge, okay? The fact that the sun is in the center, the mass of it is so huge that it is causing a gravitational force to pull the planets towards it, okay? Because gravitational force is an attractive force between all material objects. Any object that has mass exerts a gravitational force that pulls nearby objects towards itself. So we talked about that before in science class, guys. Everything has gravitational force, okay? If my mass is bigger than something else, it's going to have a gravitational force bringing the object towards me. However, we don't see any of that because the gravitational force is such a weak force that it can't actually move anything towards me, okay? Here I am with my telephone in front of me. My mass of myself is way bigger than the mass of my telephone, but the telephone is not moving closer to me because the gravitational force is so weak, it cannot. But then when you get into the universe and the sun's mass is way bigger than anything else, then yes, it's actually going to have power to pull it toward you, okay? So that is gravitational force. Then they talk about gravitational potential energy because we talked about it. The force produces potential energy. So what is that? You look at page 121. The potential energy of gravitation is the potential energy that an object gains from the work used to move it against a gravitational field. The strength of a gravitational field is the acceleration of gravity. What is the acceleration of gravity? You need to make sure you understand this. We talked about it before when we talked about acceleration. Okay, when they ask you, because we're about to use this formula, for G, the gravitational strength of the gravitational field, you're going to use 9.81, okay? Remember, I'm just giving you an introduction. You got to go back and read and process this stuff, okay? But look, there's a formula right here on page 121. EP, potential energy, EP, of gravitational force is mass times G times H, okay? Mass times the strength of the gravitational field times the height of the object. That's how you're going to find the potential energy in gravity inside that object, okay? So if you look at example 5.2, by the way, this G never changes. The G never changes, okay? So don't get confused. Like, well, they didn't give me G. It's right here. Look at 5.2. A 0.53 kilogram ball is lifted 2.4 meters above the ground. A, what is the ball's gravitational potential energy, pardon. Okay, this part is easy. It's just straight up formula. We're looking for the potential energy, so we're going to go E equals, the mass is 0.53, The G is 9.81, like I told you, it doesn't change. And the height is 2. Okay? One thing I'm going to mention to you is that this right here has to be in kilograms. Okay? So if it's not in kilograms, we need to convert it into kilograms. We don't talk a lot about units, but I do want to tell you that part. You need to have that in kilograms. So I'm going to show you that in one of the practices. Okay? So it's easy to calculate the potential energy, 0.53 times 9.81 times 2. You're going to get 12 joules or 12.4 or something like that. Joules of potential energy. But now, like I told you at the beginning of this thing, you have to convert potential energy into kinetic energy for the ball to actually move. So the ball is 2.4 meters above the ground, okay? Gravity pulls things to the earth, right? So there is a potential energy that when you drop the ball, it's going to want to fall to the earth, okay? So it has 12 joules of potential energy sitting there because of the height from the earth and because of its mass, okay, and because of gravity. So look at letter B. If the ball is dropped, what is its speed immediately before it hits the ground? Assume that it falls freely with no drag, no air resistance, okay, because that's how we do things in science, and we don't bring that in yet, right, the air resistance, but we know that it exists, right, but it's going to change. It's going to lessen the potential energy, right? But what are you doing? When you drop the ball, you're converting the 12 joules of potential energy into kinetic energy, right? Into kinetic energy. If you're not talking about air resistance, you didn't lose any kinetic energy. So you're going to do your kinetic energy formula now, using your potential energy as your kinetic energy because you converted potential energy into kinetic energy. Now, from A, they actually tell you that it's 12.5. So we're going to use the 12.5. So now I'm using my kinetic energy formula, you guys. So listen carefully. Once you drop the ball, you're using kinetic energy. You use your kinetic energy formula, but you put in your potential energy answer. Okay? The mass of the ball stayed the same, which is 0.53. And now you're looking for the velocity. So what are you going to do? You're going to multiply these two things together and divide it over here and then square it, right? V is going to become, let me see if I did it here. Did I do it? Looks like no. Okay, but V is going to become 47.17. Okay? Because like I said, you multiply this times this, divide it over here, and take the square root because you got to get this square thing over here. And you should get 47.17. Oh, pardon. Take the square root of 47.17 and you should be getting 6.9. Okay? 6.9. So that is how you convert kinetic potential energy into kinetic energy. It's sitting there, it's waiting to be used, it just needs to be transferred, converted. So look at page 122. Let's do the practices together. Okay, we're going to do the practices together, but I want you to write them down in your notes. Look at number 1. Calculate the potential energy of a 3-kilogram bag that is lifted 2 meters above the ground. So remember, our potential energy formula is EP equals mgh, right? The m here is 3 kilograms. G is 9.81, and height is 2. So when you multiply all those together, you're going to get 88.29. Okay? 88.29. I think. Let me just check that. I knew that looked funny. No, it's 58.86. I'm like, that doesn't even look like what you could get from those numbers. 58.86. I don't know what I put in my calculator last night, but 58.86. That's number 1. Number 2, an object has a 12 joules of potential energy when it is lifted 0.8 meters above the floor. What is its mass? Okay, so now again, use the formula EP equals mass GH. It has 12 joules of potential energy. We're looking for the mass. G is 9.81, and the height is 0.8, right? So you multiply 9.81 times 0.8, and you divide that over here, 12 divided by that number, and your mass is going to be 1.53. 1.53, okay? That divided by these two multiply together to get m by itself. And number 3, a 145 gram ball. So all of a sudden you see gram ball, you need to convert that into kilograms. If you have 145 grams, there's 1,000 grams and a kilogram. So what are you going to multiply by? You have 1,000 grams here to 1 kilogram. So you're going to divide 145 divided by 1,000, and you're going to get 0.145 kilograms. Okay, that's the first thing you need to do is convert it into kilograms. It's thrown straight up. It reaches a height of 4.3 meters above the ground. How fast is it traveling when it hits the ground? Okay, so first you need to start with potential energy. You need to find what the potential energy is when it gets up in the air, right? So you have the mass is 0.145. The grams is 9.81. Pardon, the grams. The G, strength of gravitational field, is 9.81. And the height is 4.3. Right? Okay, you get that first, and you get 6.166. That's your potential energy. Now we're going to convert that potential energy into kinetic energy to see what the speed was, right? So now we have E equals 1/2 mv squared. Our E is 6.16, 116, 1/2. Our mass is 0.145, remember? And we're looking for our velocity squared, okay? So again, you multiply these two together, you divide over here, and you take the square root, and you're going to end up getting 4.59 for your answer there. Okay, that's how you do the math of converting potential energy into kinetic energy, and I didn't want you to do that alone. I wanted to make sure that you completely understood it, okay? Then we see that the next one is the weak nuclear force, okay? That is on subatomic particles, the neutrons and the protons and the electrons, having a gravitational force on each other, not with the nucleus, okay, but on each other. And you're going to read a little bit more about that there. It's a weak force. Then you have the electromagnetic force. Okay, guys, this one is basically, I would say, the most common force that you're going to see, okay, and an interesting one, okay? Look what it says. I'm going to read through a lot of it with you because I want you to understand this. Both electricity and magnetism have been known and recognized from ancient times, but not until the 19th century did scientists discover that these phenomena are related. So in an electromagnetic force, you have electricity and magnetism working together. Scientists now know that any electric current produces magnetism, and that all magnetism is produced by the movement of charged particles. Okay, so electricity produces magnetism, magnetism produces electricity. They have a direct correlation with each other. And they make up electromagnetic force. Look what it says in the next paragraph. The electromagnetic force is the second strongest fundamental force. It is about 717 times stronger than the weak nuclear force and more than 10 to the 36 power times stronger than gravitation. Unlike gravitational force, the electromagnetic force affects only objects with an electric charge. So remember, there's gravity in all objects according to the mass, but only electromagnetic force is given on objects that have an electric charge, which is more than you think, guys, because of electrons, okay? Like gravitational, the electromagnetic force has a theoretically unlimited range. However, the long-range effects of the electromagnetic force are generally not important because the objects in the universe have no overall electric charge. The gravitational force always attracts and never repels. In contrast, the electromagnetic force can either attract or repel. Okay, gravitational force always pulls you towards something, okay? But electromagnetic force can either, magnets can either pull you towards something or repel you away from something. So did you know, this is the paragraph I want you to really read and understand. The next one. This is so cool. I never knew this. Guys, if gravitational force is pulling you toward the earth, right, why don't we just go through the floor? And I think you guys have asked me this before, right? Why don't we just go right through the piso and into the center of the earth if gravitational force can pull us to the ground, but it can't pull us past the ground? So listen to this paragraph. The electromagnetic force is responsible for all known forces in the universe except for the gravitational force and some subatomic forces. Most forces observed in daily life are caused by a repulsive electromagnetic force between electrons, negatively charged particles, and atoms. For example, if someone pushes a box across a room, the repulsive electromagnetic force between electrons in his hands and the electrons in the box is what actually causes the box to move, okay? Because look, when you go to push the box, your hand doesn't go into the box. Your hand pushes it. Why? Because there's repelling electrons pushing against your hand, so much so that you guys are fighting to get the box across the room, but it's fighting so that you don't get your hand in the box. So it just moves the whole box. Repulsion between electrons in his feet and electrons in the floor prevents gravity from pulling him through the floor. So there's repelling electrons on the floor that are pushing against us when we're standing on the floor, and there's repelling electrons in our feet pushing against the floor so that they're fighting against each other, and that's why we don't go down into the floor. That is cool, okay? It's why your muscles contract. Look what it says. Your muscles contract through electromagnetic interactions between molecules in the body cells. Even light and other forms of electromagnetic radiation are related to the electromagnetic force. Many manifestations of the electromagnetic force have no meaningful way to define potential energy. Despite this, there are several types of potential energy associated with it. Okay, so you have electric potential energy from electromagnetic force. You have magnetic potential energy. You have chemical potential energy. And you have elastic potential energy. Okay, and you need to read through all of those to understand them. And then you're on page 123. You have the strong nuclear force. This one's understandable, and I'll let you read that one by yourself. So look at section 5.3, because this is where you're going to get the information you need to write down today. The questions are great in section 5.3, so I'm not going to make you do more than that, but I do have requirements on how you answer them. Number 1, you need to answer with 2 sentences describing that energy. Okay? Number 2, this is where you're going to make an outline. Okay, so number 1, 2 sentences. Number 2, you're going to make an outline of the 4 fundamental forces from strongest to weakest. From strongest to weakest, so you need to start from the strong nuclear force and work your way down. But I want information in an outline form for number 2, and you need to define every bold term, every black term. So what is strong nuclear force? Nuclear potential energy. Then you go into electromagnetic force. Tell me what it is, then do electric potential energy, magnetic potential energy, chemical energy, and elastic potential energy. And go through like that. So that's why I gave you all that information I just talked about, so that you know how to do that. Okay? Number 3, number 4, and number 5, they're just answers with 1 word, 2 words, or 3 words. Okay? And then you can do number 1 and number 2 now that I did the practice with you for the application. There you go, guys. Have a great day.